Right, week 12. Is it week 12 already? So week 12, transformer. Yeah, so transformer, it's so everything we've learned so far, it all amounts up to actually learning transformer. All the RNNs and sequence to sequence, the attention and all that, it's all now coming up, like converging towards this architecture transformer, which is basically the only architecture used in the NLP these days. All right, so yeah, today's contents. First, we're gonna take a look at what the self-attention is, because after all, what transformer is just this self-attention surrounded by some tricks and feed-forward networks, and then you repeat that process several times. So in this case, in the original transformer, 6 times, in GPT-3, 24 times. So it's if you know self-attention, then you know transformer. And then we're going to take a look at the transformer, then positional encoding, and then sequence to sequence with transformers at the end. Yeah, it's not that a lot of a content, so hopefully we can end by 12 o'clock. So what is self-attention? So self-attention or transformer was proposed by Vaswani et al. A lot of people from Google basically in 2017, and the name of the paper was "Attention is All You Need." It's like the Beatles song, "All You Need Is Love," but not love, attention. So attention is all you need. And the essence is, let's use attentions to handle sequences, and only attention. So before, what we did with sequences is either using RNN or 1D convolution. But in this case, they wanted to come up with a new architecture, which only relies on attention mechanism to handle or to encode a sequence. So the name is self-attention because here, if we're given a sentence, "I like going to movies," then each word takes turn and gives or distributes attentions to other words, or in this case, you can think of them as tokens actually. So I gives attentions to all other words like this, and then in turn, in the like turn here, like gives attention to all other words, and you repeat this process for all words. So in this case, there are 6 words. So 6 words, 6 times. So that means there are 36 attentions. So it's always a square of the number of words actually. So the essence or the core part of the self-attention process is the Qkv operation. So it's called Qkv operation because there are Q and K and V involved, or it's called scale dot product as well. Before we go into the details, the high-level overview of Qkv operation looks like this. So the equation is this, but you can break this down into this part and this part. So this part is this matrix here, and V is just word embedding. So what this part does is the attention map or attention distributions. So first row is the row of first row represents the attentions distributed by the word I. So I is giving 0.5 attention, so 50% of the attention to itself, 10% of the attention to like, and 20% the attention to, and 20% attention to movies. So this is like I like going to movies and EOS. This is also I like going to movies EOS. Right. So in the second row, now it's like's turn, and like is giving 20% of the attention to I and 60% of the attention to itself, and then 10% of the attention to movies. Actually, this doesn't add up to 1, so this should be like 0.2. Yeah, of course, this is attention, so each row should sum up to 1. So it's just having 6 different sets of attention. The attention from I, the attention from like, the attention from going, the attention from to, 6 times. So now you have this. Now this is this is matrix multiplication. So you multiply this attention map with the embeddings V. So what happens is you take this row, multiply by this embedding, and you get this. So what happens is 50% times I, 10% times 50% times I, 10% times like, 20% times two, 20% times movies. So that is the product of the first attention multiplied by the embeddings. So the second one, so yeah, the second set of attention is multiplied by V, the embeddings, and you get another set of the output. So in this case, 20% times I, 60% times like, it should be 2. So 20% times movies. So what happens is you have 6 different sets of attentions, and consequently you get 6 different outputs. So this is the output of the attention, self-attention Qkv operations. So if you think about it, it's very similar to a graph convolutional neural network, which we'll talk about in the 2 classes from now, actually. So let's look at this one by one. So what Q and K and V's are. So this is called QKV because Q represents queries. So Q means query, K means key, V means value. So you can think of a lookup table actually, or lookup table or key values. A key value database like Tokyo Cabinet or Kyoto Cabinets, that kind of stuff. If you're familiar with like databases, so when you have a database or a lookup table, you look up the contents by sending a query to the database, and then so there's a database. There are keys, and there's corresponding values. And then you have a query that you want to send to this database. So it's as you have query, you match your query with all the keys like this, and see which key is so which key is like the same stuff with your query. So which key matches to your query, and if there's a match, then you retrieve the corresponding value. You retrieve. So if that's the key that's the how we operate on top of the key value storage or key value database. And in the same spirit, when you're doing self-attention, you have the queries, you have the keys, and you have the values. And that's because, so first of all, we can think about this later. First of all, so the situation is you're giving you have 2 words as input, which is thinking and machines. Oh, by the way, this illustration is copy pasted from this very wonderful blog. Actually, if you you don't even need to listen to my class, because you can just go to this website and then just take a look at all the the material, and you'll get a perfect understanding of transformer actually. So anyway, so the situation is you have 2 input words, and you want to apply self-attention on top of those 2 words. So 2 words, thinking machines. Each word is embedded in 4-dimension vectors. So it's a 4-dimensional representation vectors. So 4-dimensional vectors here. Each word has a QKV set. So there's QKV here for thinking and QKV here for machines. So QKVs for the first word is Q1, K1, V1. And QKV for the second word is Q2, K2, V2. And how you obtain them is you have a separate learnable parameters here, WQ, WK, WV. So you multiply thinking with so X1 with WQ, and you get Q1. And you multiply X2 with WQ, and you get Q2. And it's the same manner. So you multiply X1 with WK, get K1. Multiply X2 with WK, get K2. You can do that because this is 4-dimensional. This is 4. This is 4. This is 4 by 3. And then, of course, you get 3-dimensional vector output. So yeah, so there's Q1, K1, V1, Q2, K2, V2. And as I said, Q represents queries, K represents keys, V represents values. So what you do with them is you want to calculate the attention scores between them. So when it's thinking's turn, so as I said before, every word takes turns and then distributes attention. So it's thinking's turn. It's the turn for the first word, thinking. And what you do is, in that case, Q1 becomes the query because it's thinking's turn. So thinking is querying to other words, of course, including itself. So you fixed Q1. So Q1 is fixed. So Q1 is fixed. And then you match Q1 with the keys, which is K1 and K2. So you match Q1 and K1, Q1 and K2, simply by doing a dot product between them. And then you get a matching score, which is 112 points and 96 points. So that's the matching score. And then you want to convert it to a probability dense distribution, because we want to do attention. You want to do attention. So you simply convert the score 112 to 0.88, 96 to 0.12. And in between, in the intermediate stage, you divide this score with divide the score by 8, which is actually the square root of dk. Dk being the size of the vector, size of the key vector here. It doesn't. So this is just an arbitrary choice, because it doesn't have to be the size of the key vector. It could be the size of the Q vector. Size could be the size of the value vector. It doesn't really matter, because usually all these have the same dimensionality. And the reason that this value is 8 is because in the original transformer paper, they set these to be 64-dimensional vectors, like Q, K, V. These are all 64-dimensional vectors. So you put a square root on top of them, and then you get 8. So you divide. So as per this equation here, you divide the score by the square root of dk, which is 8. So you get divide by 8, and you get 14 points and 12 points. So you do this because you don't want this score to blow up. So you don't want these scores like 112 and 96 to blow up as you use larger vectors for QKV. Because this is a dot product. So if you do a dot product between 64-dimensional vectors, then it'll amount to some value. But if you do a dot product between 1,000-dimensional vectors, then surely that value will is a little more likely to blow up or cause instability, basically. So that's why they normalize the score into some smaller values by dividing it with square root of dk. So you're given 14 and 12, and then you apply softmax on top of them, and then you get 0.88 and 0.112. So 88% and 12%. So that's how you get the attention distribution. 소프트맥스인데. 네, 제가 말씀드린 대로 애초에 요 점수가 너무 커지는 걸 방지하기 위해서 나눠주는 겁니다. 이게 64차원짜리로 내적을 할 때랑 1000차원짜리로 내적할 때랑 10,000차원짜리로 내적할 때랑 다 그 내적의 값이 너무 달라지기 때문에, 그래서 이제 그거를 맞춰주려고 이제 일부러 노멀라이즈를 해주는 거예요. 네, 넘어가겠습니다. Alright, so that's these sets, these two values of attention probability, attention scores or probabilities. It's the attentions from attentions given by thinking. So you want to do the same thing with you want to do actually we haven't there's no slide for that, but you want to do the same thing all over again with machines, but this time you want to fix Q2. You want to fix Q2 and then do a dot product with K1, Q2 with K2, and then get the score. Get some scores, normalize it. So normalize it, and then put them into the softmax, and then you get another set of attention scores, which is attention scores from machines. So I think keep that in your mind, and then you're right. So you have the softmax scores 0.88% and 12%, and then you simply multiply these two scores to the corresponding values, because if you think about the key value thing here again, you have the key, then you need to retrieve the value. So it's the same manner. So You have the key. You have so you found the matching keys. Well, this is not exactly a hard match. It's a soft match because you're doing 88% and 12%. So you're basically doing a weighted sum. So you multiply 88% to the vector, to the value embedding here, and 12% to the value here. So each to V1 and V2, and you weight sum them, and then you get Z1. So Z1 here is basically 0.88 times V1 plus 0.12 times V2. So that's how you get Z1. And the same manner as Z2. So as I said, you have a separate set of attention values originating from machines, and then you do the same weighted sum operation, and then you get Z2. So the important thing is, given 2 words, you get 2 outputs. So you get the same number of outputs as the number of inputs, basically. And another thing to note is that the output doesn't have to be the same, doesn't have to have the same dimensionality as the input. So because the input was 4-dimensional, but the output is the same. The output has the same dimensionality as the Q and K and V. Right. So yeah. So what this is you want to do it all at the same time. So here, what I described is you first do a attention operation for thinking, and then you do another operation for machines, and then you get Z1 and Z2. But that's basically doing a for loop, and the for loop being like, the for loop over the input tokens. But the reason that probably the biggest reason that Google people came up with transformers, because they were not happy or satisfied with the speed of RNN, where you have to put each word one at a time, because RNN is a sequential model. So you have to put the first word in order for you to be able to put the second word, and then you can put the third word, and then you can put the fourth word. So you need, no matter what, you need a for loop over the words. But if the input sentence becomes longer, then the for loop takes longer, and the Google people were not happy about that. So they came up with a way to process all the words at the same time, just in a parallel manner, using GPU, basically. So if you do attention for thinking, attention for machines, then that's basically going back to the for loop again. So what you want to do is you want to parallelize them by using a vectorized format. So this is the first word, thinking, and this is the second word, machines. So basically, you put them together, you stack them together like a matrix, and then you multiply them with WQ, K, V in order to get the Q1. So this is Q1, this is Q2, this is K1, this is K2. Basically, yeah. Oh, sorry, this is V1, this is V2. Yeah. So in this manner, you get the Q's and K's and V's all at the same time for both words, and then you do this vectorized format attention Qkv operation instead of doing Q1 fix Q1 multiply with K1 K2, fix Q2 multiply with K1 K2. You don't do that. You simply just do Q and K transpose, multiply them, divide by the square root of dk, then softmax, do the softmax. This part is how you get the attention matrix or attention map, and then you multiply them with V, and then you get the Z's. So all at the same time. 그런 관점이라면 소프트맥스는 가만히 놔뒀을까? 소프트맥스도 ON 아닌가요? 소프트맥스가 ON 이런, 소프트맥스는 안 할 수가 없을 텐데. 소프트맥스, 그러니까 이제 이걸 어텐션을 만들어주기 위해서 소프트맥스를 무조건 해야 되고, 대신에 소프트맥스를, 그러니까 이제 첫 번째 단어에 대해서 소프트맥스 한번 걸어보고, 두 번째 단어에 대해서 소프트맥스 한번 걸어보고, 그러는 게 아니라 전부에 다 해서 거는 거예요. 그래서 얘만 따지면 얘도 사실 매트릭스가 나오거든요. 여기다가 이제 소프트맥스를 전체를 다 걸되, 이 엑시스, 이게 이제 엑시스 이게 0이고, 이게 이제 엑시스 1인데 이제 엑시스 1에 대해서 소프트맥스를 걸어주는 겁니다. 이 전체 매트릭스에 대해서. 그러면 이제 매트릭스 한 번에 다 되는 거니까. 그렇게 해가지고 이제 normalized attention 매트릭스가 나오고, 그거 이제 V랑 곱해주면 됩니다. 네, 알겠습니다. 네. All right, yeah. What I just said is, So this is already a matrix. This is already a matrix, but it is a normalized matrix. It's not a probability matrix. It's some like a score matrix, and you want to normalize them by applying a softmax on top of them like this. Actually, this should be 2 by 2. So I'm sorry about that, because there are only 2 words in this example: thinking and machines. So it's 2 by 2. And then you want to apply softmax in this direction. You want this to sum up to 1, this to sum up to 1. So you want to apply softmax on the axis 1, right? Okay, so this is how you get the this is a vectorized format of Qkv operation. So obviously this is way faster than doing a for loop over each word, because you process all the words at the same time. So yeah, so now you get the idea why this is why this works like so. So like this part being this part being this, and then the output, the z's being this. So this is self-attention. So because you can, and again, you can see why it's called self-attention, because in the original sequence to RNN sequence to sequence model with attention, the attention was given from the output word, which is, for example, if you're doing a French to English. So this is you put French, you put French into the encoder, and then you get the English from the out decoder. So this is encoder, this is decoder, and the attention was given from decoder to the encoder, basically. So each word in the English, when you generate each word in the English, the attention was given like in this manner, like this. But now there's only a single sentence. There's no input and output. It's just given this input sentence, I like going to movies, you do an attention within itself. So that is why it's called self-attention. All right, moving on. So okay, so we're moving on. So now that we've learned self-attention, we are moving on to something called multi-attention. 로스를 어떻게 정해야 셀프-attention 학습할 수 있는 건가요? 그거는 어떤 로스를 정하든 알아서 학습이 됩니다. 이게 원래는 요거가 이 트랜스포머가. So the question is, how do we set the proper laws to, you know, properly train this self-attention? So the answer is, whatever you want to do, it'll just, whatever laws you set, self-attention will just, you know, work accordingly, learn accordingly. So originally, transformer attention, the paper "Attention is All You Need" was proposed for translation. Again, this was proposed in the context of translation, and simply the Google people, they wanted to do a translation way faster than using RNN. So the essence of translation is actually just a encoder and decoder. There's encoder, there's decoder, and there's input, some sentence, and then there's output sentence, and the encoder and decoder are connected. So the essence is this, and what you use to compose the encoder is really a matter of choice, because you can put RNN you can use RNN to compose your encoder, or you can use 1DCNN to you know, implement your encoder, or you can use transformer to implement your encoder. Decoder, the same story with decoder. So it doesn't really matter, and so you do. And the self-attention is basically just a way to encode a input sequence. So whatever you do with the encoded sequence, it's up to you, and the self-attention will learn accordingly. If you do translation, then self-attention will be trained to perform translation well. If you do, I don't know, what else are there? If you do, let's see, conversation, for example, if you are training a chatbot, then the self-attention will, you know, learn to have conversation well. It basically doesn't matter whatever you do. It's just a tool, self-attention. Just like having like an RNN, you can do anything with RNN. You can do like sentiment classification, you can do translation, whatever. It's the same thing. A transformer is just a tool for encoding a sequence. All right, moving on. So we're moving on to a multi-attention, and the core idea is that you want to have a multiple self-attentions at the same time. So here you can look at the self-attention map, and previously we had just one map using one Qkv operation, but maybe you want to have a separate, maybe you want to have like two attention maps. So there's another map behind the first map. And in this case, then you can have two sets of attentions, even from the same word. So this is the attention from I, but the I's attention, there can be another set of I's attention. So each word now has a multiple sets of attentions, and there are multiple words. So now we're having like way more number of attention distributions. So yeah. So if you do Qkv operation, so this is another set of V. So V prime. This is attention map AM. This is attention map prime. And you do Qkv operation, you get two sets of outputs, two sets of Z's. So this is the first output, this is the second output. And the reason why we want to do this is basically you want to increase the power of your transformer. So if you use just one attention map like this, if you just use one attention map, then you can only learn one semantic information for each word. Like I can have only a fixed set of attentions. Like this is the only option, this is the only attention, or this is the only expression that I can learn. But if you have another set of attention, then the I can learn another set of expressions, Like maybe in the first attention map, I will focus on itself, like 0.5 here. But maybe in the second map, I will focus more on on the verb. So this might be 0.5 and this might be 0.1, So like each attention map has different roles, basically. So yeah, so mathematically or implementation wise, it's just copy and paste. Actually, you have just Qkv. You just do two Qkv operations and that's it. So there's one set of Qkv operations. There's another. So you have one set of Qkv, another set of Qkv, all in vectorized format. And then if you have, for example, in this case, there are two sets of Qkvs, but in the original transformer paper, they use 8 sets of Qkvs. So there are 8 outputs, Z0, Z1, all the way to Z7. So what they're doing is they're doing 8 times of Qkv operations. So that's why they get 8 outputs. So it's very expressive. And what they do is after they've obtained 8 sets of Z's, you multiply them with a real humongous, like a very vertically very long output. Basically another you do another linear operation to put these very long concatenated Z's into the original size, which is 4-dimensional, because your X was also 4-dimensional. So no matter how many heads or how many Z's you have, it's the same thing. Like head is like the Z. So no matter how many Z's or heads you have, you want to put them into the original size in the end. So that's why this whole thing is here. So if you have 8 heads, then each Z's have 2 by 3. It's a 2 by 3 matrix. And if you have 8 outputs, then you basically have 2 by 24. So this is 2, and this is 24-dimensional. So, and you want to put them back to the 2 by 4-dimensional matrix. So you have a 24 by 4 learnable parameter to put these back into this original size. 같은 인풋에서 서로 다른 어텐션을 어떻게 얻을 수 있는 것인가요? 그거는 보장은 없어. The question is, how do you guarantee that this attention map and this attention map will have like different distinct values? And there's no guarantee. It's just like using different number of filters in convolutional neural network. Like in convness, you use like 64 kernels, 64 filters, or 128 filters, or 256 filters. And there's no guarantee, as I said, that different filters will learn different stuff, but they tend to do so in order to maximize some performance. Each filter tends to learn slightly different stuff. So it's the same thing here. Each attention map will learn slightly different stuff in order to maximize some task performance. But of course, there's a diminishing return. If you increase from 1 to 2, if you increase from 1 to using one attention map to 2 attention maps, then you see some increase in the performance. But if you increase from 16 to 32, then you don't see a lot of You don't see a lot of increase basically. So I think in BERT they use 12 attention heads, so 12 is like enough already. All right, moving on. So yeah, so the whole process of multi-head attention looks like this. So there's the input could be either a input word vector, or it could be already an embedded word vector. So after this, what you're gonna see is you're gonna repeat this Qkv operations again and again and again. So you get z's from. So the first input, the first block will receive the words, the raw words or raw word embeddings, and then it'll output some z, which is this. But then the second block will receive this z and then output another like modified z, and then you'll repeat this process. So in the anyway, yeah. So that's why this R is here. Like, you know, the input could be either the raw word embeddings, or it could be another embeddings from the block beneath the current block, basically. Anyway, so here let's look at this part. So given two word embeddings, you have eight attention heads. So one set of QKVs, another set of QKVs, another set of QKVs. I mean QKV, like learnable parameters. There are 8 sets of learnable parameters. That's how you get QKV zeros, QKV ones, all the way to QKV sevens, because there are 8 heads. There are basically 8 heads, and then each head will produce Z0, Z1 all the way to Z7, and then you concatenate them and then linearly compress them using this WO learnable matrix, and that's how you get the final Z. And then if you and then you can put this into the next block, the next Qkv operations. If you want to do self-attention 2 times, you can put this into another self-attention block. If you want to do it 3 times, then repeat this process again and again and again. So it's not a complicated model. You basically, once you've implemented the Qkv operations as a Python function or PyTorch function, then you just need to copy paste it over and over again. So hopefully you can imagine how you would implement this whole thing in PyTorch. So the good thing about the attention and all that is because it's interpretability. Like, as we've looked at the attention maps between the French and English sentences in the sequence to sequence example, we have a bunch of attentions now. So there are like a whole lot of attentions we can take a look at. And this is self-attention, so you can. So here there are some additional information. This is layer 5. So as I said, the original transformer, there were 6 layers in the encoder. There were 6 layers in the encoder, and there were 6 layers in the decoder. So this whole thing was encoder. This whole thing was decoder. And each block had its own self-attention component. So there are basically 1, 2, 3, 4, 5, 6. I'm sorry, 1, 2, 3, 4, 5, 6 self-attention components. And we're looking at layer 5, which is the top layer because we start from 0. So layer 0, layer 1, layer 2, 3, 4, layer 5. So layer 5 has its own self-attention, and it's not just self-attention, it's multi-head attentions, because each block has multi-head attention. So on the top layer, and we're looking at the input to input self-attention. So the input sentence, and there are 8 attention heads. So there are 8 attention heads here. So this is attention head 1, attention head 2, 3, 4, 5, 6, 7, 8 attention heads. And currently, I think we're looking at the second attention head, because this is orange and this is also orange. And this attention is given by this word, it. So the sentence is, the animal didn't cross the street because it was too tired. And the attention given by it in this particular attention head looks like this. And you can see that a lot of the attention is put upon these two words, the animal. So it is actually the animal itself. The animal didn't cross the street because it was too tired. It is actually the animal, because the animal was too tired, so that's why it didn't cross the street. So obviously you want it to point to what the actual content. So it is a pronoun. So this is like anaphora resolution. I'm not sure if you guys are familiar with anaphora resolution. It's just like, resolving the true identity of the pronouns, basically. Yeah, so this is attention head 1. If you look at attention head 3, so this is attention head 1, this is attention head 3, because this is green, and now this time it is pointing towards tires. So that's, again, it's a valid dependency because the animal was to tires. So this is like a predicate, like the verb, or in Korean, 서술어. And if you start adding all the attention heads, like everything together, then now it's kind of hard to see what's happening. Like in the first attention, the second attention head, basically, so this attention head was resolving pronoun, and this attention head was pointing towards predicate. But if you start looking at all the attention, eight attention heads, then it's kind of tiring to see which is which. So you, sooner or later, you just you give up on trying to interpret what's going on here. 레이어와 헤드 어떻게 다른 건가요? 레이어는 이제 요거가 레이어고, 이제 1 레이어 1, 2, 3, 4, 5, 6이고, 한 레이어 안에 셀프 멀티 헤드 어텐션 블락이 하나씩 있어요. 그래서 이제 한 레이어 안에 헤드가 여러 개씩 있다 보시면 됩니다. 요거는 이제 그 다음 장에 가시면 이제 확실히 아시게 될 거예요. Alright, so this is the multi-head. So this is the end of the self-attention, multi-head attention, and now we're going to the transformer now. Now you've looked at the core component. Now we are ready to blow it up to multiple blocks. So as I said, transformer was originally designed for translation. So it has encoder decoder architecture. So in this case, French in, English out. French in, English out. And as I said, you can implement your encoder and decoder with whatever architecture of your preference, RNN, CNN, whatever. But in this case, we're gonna compose it with transformers, and especially 6 transformers. So there are 6 blocks basically. There's 1, 2, 3, 4, 5, 6 blocks in the encoder, 6 blocks in the decoder. And first of all, we're gonna look at encoder only. So the architecture of encoder and decoder are very similar. So if we're going to first take a look at the encoder and then try to look at the decoder in the next stage. And as I said, this is a repetition so 6 repetition of a single encoder. The architecture is all the same. Like each encoder has exactly the same architecture, although different weight parameters, but their architecture, their structure is exactly the same. So you just copy paste 6 different blocks. So all you need to do is just take a look at one single encoder. It's like the inception net. Inception net, you had a single inception component and then you repeated it multiple times. So it's the same architecture here. You have a single encoder and just repeat this. You copy paste it 6 times. So a single encoder looks like this. So in this case, there are 3 input words, 3 input French words. There's self-attention component, and then after the self-attention component, there will be the same number of Z's as the number of input words. So 3 words in, 3 Z's out, and then you put another feed-forward network on top of the Z's just to give a little boot, a little more, extra boost in the expressiveness of the encoder. So the basic flow is you have the input words, put it through a self-attention, you get the same number of Z's, and each Z is put through the same feed-forward network. There's only one feed-forward network, and you just apply it to the Z's in the same manner. It's not like each Z is put to 3 different feed-forward networks. There's just only one feed-forward network, and you apply it to all the Z's, and then you get the outputs here. And yeah, so. And yeah, well, I mean, we're like jumping back and forth between like 2 inputs and 3 input words, but basically, as I said, the same feed-forward network is applied to each individual Z's, and then you get the output R or whatever output, whatever you want to call it. So the same, again, same number of inputs, same number of outputs, and then the next encoder block here will receive the same number of inputs and same number of outputs, and the block 3 will do the same, block 4 will do the same, you know, again and again and again. And as I said, this self-attention will be actually a multi-head attention. This is multi-head attention. All right. Now, a bit more into the detail. This is not the end, actually. There are a little bit more tricks put into the encoder block. Like this is all the learnable parameters there are in a single encoder block. Like there's QKV, like WQ, WK, WVs in the self-attention block, and then of course the feed-forward neural network will have its own learnable parameters. But on top of this, there are some tricks. So there are, if you fully expand the encoder, then you have the add and normalize. Let me use a red. Let me use a red pen. So there's add and normalize, and there's positional encoding. So positional encoding, we'll talk about it later today. But first of all, what we need to take a look at is the add and normalize blocks. So self-attention block and the feed-forward block we already know. Oh, I forgot to mention. So feed-forward block is usually just, you know, basically MLP, multi-layer perceptron with 1 or 2 hidden layers with ReLU activations, usually. So, and maybe you want to put a little dropout here and there as well, but the details are not that important. So we've already took a look at these two. And now it's time to take a look at the add and normalize. And basically it's called add and normalize because you actually add and normalize. So add is this residual connection. So you put, there's an input and you put the skip connection to the output of the self-attention. So self-attention is in between, and the input and output, there's a skip connection, just like the residual network, just like ResNet, there's a residual connection between in and out of the self-attention. And there's this attention. So that's the add part. And there's another add part. So another add part between so between, so there's a feed-forward network between. So input and output of the feed-forward part, there's another residual connection here and here. So that's the add part. And normalized part is basically it's normalizing using layer norm. So there's a layer norm. We talked about layer norm, like when we were talking about confidence, we talked about batch norms, layer norms, and instance norms, and this is layer norm basically. I don't know if you remember, but the problem with the limitation of batch norm is that you needed to, there's like a discrepancy between the training phase and the test phase, but layer norm doesn't have that. So that's probably why the Google people use layer norm in the transformer, because they didn't want to bother with batch norm. Okay, so the whole process is like this. You put the words, input word embeddings, and add the positional encoding to the input words, and you get this slightly different colored X1 and X2. And then you put it through a self-attention, and then you get the Z1 and Z2. And there's a skip connection here and here. So there's X plus Z. This is the skip connection here. And then you do the layer norm on top of the skip connection. That's how you normalize the outputs of your self-attention block. And you do the same for the feed-forward block. So the internal mechanism of add and normalize here is exactly the same as add and normalize here. 인풋들끼리 feed-forward 공유하는 거라고 하지 않으셨나요? 그냥 그림을 그렇게 그린 거예요. 여기, so the feed-forward here and feed-forward here, they have their weights are shared. It's not like there's different their weight parameters. So they are the same feed-forward networks with tied weight parameters. It's just that the illustration is to exaggerate or emphasize that Z1 and Z2 are handled independently. They're independently fed into the feed-forward, but it's the same feed-forward. So yeah, so the question is, can we use batch norm instead of layer norm? You could do that, but then you need to memorize, you know, the rolling mean value and the rolling average of means and rolling average of sigmas. And you want to, yeah, it's just basically a bit bothersome. What is the significance of skip connection? Skip connection is there so that you can use more layers. I'm not sure if you were there in the resonance session, but what the revolution of or the innovation of the innovation that Resonant brought to the world is the ability for the researchers to use like way deeper layer, way more number of layers than before. Like before Resonant, it was basically like 20 layers or 15 layers, and that was it. Then it was already saturating, or the performance was not increasing. But as soon as Resonant came up with the concept of residual connection, it was able to blow the architecture up to 100 layers, and even 1,000 layers, to be honest. So in this deep learning research or deep learning domain, if you want to blow up the number of layers, you need skip connections. So that's why we have the skip connections. 한 문장에 대해 인코더 돌리는 건 배치노면 어떻게 적용될 수 있는지요? I'm not sure. I haven't really given it a lot of thought. I mean, why not? The original batch norm was applied on a single inception net, so it's not like there were input and output. So yeah, I mean, batch norm is there to prevent or to remedy the internal covariate shift, if you remember. So if you do a backprop, then all the weight parameters will be shifted or perturbed, and that alone makes the model optimization process harder, or because of the internal covariate shift. So batch norm is there to prevent that, and there's no reason why we can't use batch norm here instead of layer norm. I'm not really sure. Yeah, maybe there's a paper trying to use batch norm instead of layer norm, but nobody, as long as I've seen, as long as I remember, no paper tried to swap layer norm with batch norm, because already transformer is working pretty well. All right, so okay, so yeah, so this is basically the internal architecture of a single encoder, and basically the rest is just copy and paste. You implement this in PyTorch class, the module class, and then you copy paste it 6 times to get 6 encoders. And yeah, you can easily see how you want to implement this. You have the self-attention with QKVs, and you blow it up to multi-head, and then you do layer norm with the skip connection, and then put that through the feed forward, and then do the same thing, and then you get the output. And so that's the whole, whole architecture. 네, 알겠습니다. All right, now moving on to positional encoding. So positional encoding. So this is actually important. I haven't really emphasized the role of this so far, but if you look at this Qkv operations without positional encoding, is you'll realize that there's no concept of order here. If you swap I and like the position of them, then nothing will change except that these will change. So the contents of individual z's will not change, because even when you like permute the order of the words. Like it's that the only thing affected is the order of the output z's. So if you do a permutation here, then there will be a permutation there. But the contents 0.5 times 0.1 times the contents or the values of the output z's will not change. It's the order of z's that will change. So it means that this is permutation invariant. So there are no concept of order. So this is actually self-attention is a set encoder, not a sequence encoder, if you think about it, because this is permutation invariant. So if you actually in the future whatever research topics or whatever, if you need to encode, like process a set of items, a set of distinct items, then using self-attention is a good idea, basically, because it's a set encoder. Inherently, it's not a sequence encoder. So if you want to make this into a sequence encoder, you need to somehow tell the model that there are orders between these words. Like this is the first, second, third, fourth, fifth, sixth word. You need to inject the order information into the model. So that is why we have positional encoding. Without this, there's no concept of order. So if you have G, suis, étudiant as a French input words, then you want to tell the model that this is the first word, this is the second word, and this is the third word, and that's where positional encoding comes in. So when you have a positional encoding, then this vector represents the first position, this vector represents the second position, this vector represents the third position, and you simply add these to the original word embeddings, and then you get the slightly different colored x1, x2, x3. So this is the embedded word embeddings embedded with time signals. All right. So how do we implement the positional encoding? So there are certain requirements to positional encoding, like, because what you can do is actually you can just simply set T1 to be 0001 and T2 to be 0002 and T3 to be 0003, just to indicate that this is the first word, second word, third word. Like there's nothing that prevents you from doing this actually. So there are a million different ways to inject the order information, but there are certain requirements that you want to satisfy. So the first is the positional encoding should output a unique encoding for each time step. So like the first word and second word should have unique output. It cannot be that the first word like T1, it cannot be that the first T1 being 001 and T2 to be 0001. Then there's no, like, this serves no purpose at all. So this is an obviously obvious requirement. And the second requirement is distance between any two time steps should be consistent across sentences with different lengths. So for example, the distance between the first word and the second word, and the second one and the third word should be the same. It's the same one word apart. So that should not change basically. And this is the same with the second word and the fourth word, or sixth word and eighth word. Like, doesn't matter where you are, doesn't matter how long your sentence is, the distance between two given words should be preserved across different parts of the sentence. Third is, our model should generalize to longer sentences without any efforts. Its value should be bounded. So so it means that your positional encoding algorithm should have no limit to the input sequence length. So it should, so for example, if you've trained your model with 20 length sequences only, and then suddenly in the test phase you are given 30 length sequence, and then your positional encoding algorithm breaks, it gets broken, then that's not a good encoding algorithm. And it must be deterministic. Of course, if your positional encodings are probabilistic, then there's no reason to use positional encoding, basically. All right. So all these requirements, if you keep this in your mind, and then there are two example positional encodings. One is, so given dark horses are faster than white horses, given this 7-word sentence, first encoding scheme is just putting 1, 2, 3, 4, 5, 6, 7. So this is just absolute position. So this is positional encoding 1. And another positional encoding 2 is you set the boundary between 0 and 1. So there's 0 and 1, and you divide your positional encodings with the number of given words, in this case 7. So the first word is given 0.47, 0.28, 0.42, 0.56. So in this case, there are pros and cons between the two. So in this case, the good thing about the positional encoding 2 is that every time, given no matter how long your sentences are, your positional encodings are bound between 0 and 1. Compared to this. Like, for example, in this case, you're trained by sentence length 7, so you know what 7 means. But when the model is given 8-word sentence, then you suddenly need to you suddenly have a positional encoding 8, which you have never seen before in the model's perspective. So it has a poor generalization power. But if you use this positional encoding 2, I mean, second encoding scheme, then everything is bound by 0 and 1. So that's the kind of like a pro part of positional encoding too. But the same, I mean, similar problem arises. So this is training sample, this is test sample, and test sample there are 8 words. And this time 8 is so the never seen, unseen positional encoding 8 is generated by the first algorithm. So that's problematic for the model. In the similar manner, positional encodings generated by the second algorithm, it has slightly different value. This is 1.4, but this is 1.2. This is 2.8, this is 2.5. This is 8.4, but this is 8.7. So again, this is slightly different. So this is not a very nice, generalizable encoding scheme again. So these naive ones, these are like naive examples of positional encoding. So probably not a good idea. 마지막이 왜 0.98이 아닌 건가요? Because you want to add 0.14. That's just technicality. Yeah, it could be 0.9, but we want to fix the last time step as 1 all the time for better generalization than the first algorithm. But yeah, doesn't really matter. It's just an example. So a better approach is not to have a scalar valued positional encodings, but a vector valued positional encoding. So in this case, 0, like the first word could have 0, 0, 0, 0. The second word could have 0, 0, 0, 1. Third word could have 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. It's basically binary coding, basically. So in this case, you can have you can have 4 vectors representing the position values, and this has a better generalizability because this, now you're learning each parameter. So like so it's no longer a scalar value. So these are somehow put into the model, and then like each time there will, like each dimension is used in different manners. So like you can, if for example, like if you've seen until like maybe like oh, this is 10, like 10 words in the during training phase, you've seen sequence length of 10, and now you're given 13, then you can easily just plug in 1, and you can easily represent the 13th word position with 1101, and you can be done with it. So it has a better generalizability. But the problem is this is binary encoding, so it has it's major waste of space. With 4 vectors, all you can do is represent 16 positions. So 4 dimension leads to 16 positions, which is a huge waste of space. But there's the brilliant idea by the Google people when they came up with the positional encoding is, you look at let me erase this. You look at individual dimensions here, first dimension, and you see how they change over different positions. It's 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. If you look at second dimension, then it's 0, 0, 1, 1, 0, 0, 1, 1. And if you look at third dimension, then it's 0, 0, 0, 1, 1, 1, 1. So the change of the rate of change or the frequency is different for each dimension. So the first dimension has the highest frequency. Second dimension has a relatively a lower frequency, and the third dimension has even lower frequency, and the fourth dimension has the lowest frequency. This first dimension, its value changes every word, like this, and the second dimension changes every 2 words, like 2, 2, 2, 2, and the third dimension changes every 4 words, 4, 4, 4, 4. So you can think about this and how to generalize it into a continuous value using sinusoidal functions. So that's basically the essence of positional encoding. You change it to a sinusoidal function. So this So this axis is the dimensionality. Instead of using 4 dimensions, we're using 128 dimensions as a representation of a position. And this is the position. Like this is the first word, like first word. This is the second word, and then all the way to the 50th or the last word. And as I said, the first dimension here has the highest frequency, and the second dimension has a relatively lower frequency. I'm sorry. Actually, the specific implementation of positional encoding is they use here the first. I think this is cosine. This is cosine. This is sine. And this is cosine, and this is sine. So the first, like every odd dimension is represented by the cosine function, and every even dimension is represented by sine functions, and with increasing frequency. So the first two has the same frequency, the second two has the same frequency, the third two, like this is the same, like third two has the same frequency, but decreasing frequencies. So the first has the highest frequency, the second has a lower frequency, the third has a third pair has a lower frequency, the fourth pair has an even lower frequency, so on and so forth, basically. So you can see that the first so you can see that the first row, the first column has the like the highest rate of change. Like so, what's the so 0? Yeah, so white is 0, blue is 1, and red is -1 because we're using sinusoidal functions. So it's like like this. Yeah, it's basically something like that. Yeah. So compared to that, like the last dimension here is just all 1, and probably at some point it'll like go down like a sinusoidal function. But the frequency is so low in the 128th dimension, it's just you rarely see it fluctuating. Right. So yeah, that's the essence of positional encoding. Yeah, so it looks like this. So it starts with sine, not cosine. I'm sorry. Sine, cosine, sine, cosine, sine, cosine, all the way back, all the way to to the 128th dimension, and the frequency is adjusted by this value. I'm not sure why they use like this particular value, but basically it's suffice to say that the frequency is decreasing as the number of dimension increases. Right. So yeah, there is rarely a case where you need to implement positional encoding yourself. There's positional encoding function from PyTorch you can just simply call. So, but is informative to know why such thing came about in the beginning. So I think this is a pretty like intelligent way to represent positions with multi-dimensional vectors. Right. So yeah. So this is positional encoding. This is a bit of a side note, like just trying to send a message or trying to tell you guys, like, doesn't matter how you. There are different ways to basically process or encode sequences. Like one way is to use. So this is the previous sample that we. So this is just words, and this is a given sentence. Given sentence, you can use RNN to encode your input sentence. And if you use RNN, you'll get the same number of hidden layers as the number of input words. If you use 1D convnets, then you can use paddings appropriately to get the same number of outputs as the number of input words. And in the last manner, transformer, it's the same. You have the same number of inputs as the same number of outputs. So yeah. So these are all different flavors of sequence encoders. And these days in NLP, people usually just use transformers only. Okay, so yeah, we're moving on to the final part, the encoder decoder part. All right, so as I said, the transformer were proposed in the context of translation, so encoder and decoder. And this part, now I hope that everybody's pretty clear with this part. So you put G sui into the, and then the same number of some Z1, Z2, Z3 will be put out here. And then somehow using this and using this, you want to use a decoder with this, along with this, and then generate an English sentence. So given French, it's trying to generate English words, and you need to use this and the decoder to properly generate the output words. And you can see the connections here, the connections between the last layer to the last layer of encoder, all the connections to each decoder, here, and here, and you'll see why. So that's because in each decoder, the decoder needs to mix the output so far, just like in the encoder decoder using RNN. You need to mix and match. You need to mix the current English words generated by the decoder so far with the encoded French words, and it's the same manner here. So you need to somehow mix with the currently with the English words there. So there will be I am a student. When you're training, these will be given into the decoder. So you need to mix and match between this and this, this and this in each decoder blocks, like this. So let's look at the details. So okay, so this is the encoder. So just a reminder, there's self-attention, add normalize, feed forward, and add normalize. Decoder has a bit more components. So it starts with a masked self-attention. We'll talk about why we call this masked later. So there's another, of course, this start with a self-attention, and there's add and normalize. Also, there still is feed forward and add normalize, but there's another block of attention here. So this is encoder decoder attention block. Encoder decoder attention block. So you need this to mix this the information from here with the information from here. That's why it's called encoder and decoder attention block. So we have one more component, and then the feed forward, add normalize. Then you're done with the first decoder block, and then you move on to the second decoder block, which has exactly the same structure as the first decoder. So you can see, you can see this information flowing into the second decoder block as well, because the second decoder block will also have encoder decoder attention. All right, so of course, this information is the English word that is supposed to be generated by the decoder. I mean, yeah, the examples come back and forth between like thinking machines and the Jesui to the end. But hope the core message is still conveyed to you guys. All right, so the decoding processes. So these are already given. The French words Jesui étudiant is given to the encoder, of course. So I mean, with it. So there's a Jesui to the embeddings, and then there's a positional embedding. There's positional embedding encoding in between here, and that's how you get these light green embeddings, and then put this to the encoder, set of encoders or blocks of encoders. Then you get the outputs, and using the output, you generate keys and values. So using the output, using these Z1 or whatever you call it, the output of the encoder, you generate keys and values that represents the keys and values of the outputs. I mean, the keys and values of the input, the encoded words, and then you use it in the decoder part. So, so for example, in the first decoding step, you generate I. So of course there will be like a start function, start token somewhere. There is a start, start token somewhere. Put the start token, and then you generate I. And then in the second step, given I, of course, there's start token hidden here. Start token here. You get the M, and then you get the and then you get the student, and then you get the end of sentence. So that's the decoding step. And at each time step, you're using the keys and values from the encoded words and mixing that with these so currently generated English words, and you'll see how it's done. What do we have that? Oh, oops, sorry, no, not this one. I'm sorry. Well, okay, we actually let me just tell you a bit more detail on how these are done in this particular part, encoder decoder attention. So encoder and decoder attention. So we are at, let's see, we are at I. So there's start. Actually, maybe let's start from here. Let's start from here. So currently what we have is the hidden start, and then we've generated I, and it's time to generate M. This is our target. And what we do in this process is we have the start and I, and they are there's a self attention here. Let's just assume that there's just a single decoder block. There's a single decoder block. There's self attention, and there's encoder decoder attention, and then there's feed forward all the way. And this part, I hope this part is clear. What happens in this component, self attention, multi-headed self attention, is you mix start and I, and that's it. So all the Q's and K's and V's will be generated based on start and I in this block, and then basically start and I, and like they are giving attentions to each other, and then you generate, and then the same number of tokens as start and I will be generated like here. There's Z. Then so let me draw it a bit more clearly. Even bigger. So self attention, and then so the start will go here, I will go here. So this is start and I, and then it'll generate Z's, Z1, Z2, and then there's encoder, decoder, attention. And that's where these come into, these K's and V's generated from this input words will play a role when they flow into here. So in this case, what happens is the English words generated so far are being the queries, and they are asking the question, or they're basically querying to the input words how important or how compatible each English word generated so far with the French words here. Just like the sequence to sequence RNN encoder decoder architecture, like when you were generating English word, you needed to mix it, you needed to see how each English word is compatible with the French words, and that's why you had this kind of this picture here, like all the French words here, and all the French words here, and all the English words here, and then there was like a heat map like this, right? There was a heat map, and basically that was English word. When generating English word, it was seeing the compatibility between all the French words, and it's the same here. When you're generating English word, which we're generating M now. When you're generating M, you need to see how compatible start and I are with each je suis étudiant. So that's what's happening in the encoder decoder here in enc attention. So in this case, obviously, queries should come from the English part, but the keys and values should come from the French part. I hope that's clear, because the English word is trying to see its compatibility with the French words. So the English words become the queries, French words become the keys and values. So there's actually another set of WK and WV, for the output of the encoder to this is how it's generated here, and these I'm sorry, maybe different color, and this and this generates V's here. And once you have K's and V's ready, you just simply use that repeatedly in the decoder process. So it's the same Qkv operation. It's the same Qkv operation. There's a Qkv operations here, but that only relies on the English words. The Qkv operations here, Q's come from Z's, K's and V's come from here, and that's the only difference. And then you have the feed forward here. So of course there will be another Z's coming, the same number of Z's come out of this encoder decoder architecture attention as well, and then you put them through the feed forward, and then you have the final Z1 and Z2 output from the single decoder, and then you have another decoder that does the same thing, another same thing, then you put it through the six times into six stacks of decoder, and then after you've done that, then you'll have right beneath the linear softmax layer, you have the same number of highly contextualized embeddings as the same number of start and I basically. And then given this, you simply do a linear. You put them all through a linear operation to make it into like a single vector, and then you get the logits, and then you put the logits through the softmax, and then you get the log probability, and then you just pick the whatever word that has the highest probability out of your softmax probability. So that is how you get M here. Like so far you had start and I, and then you put it through a decoder, get a highly contextualized embeddings, concatenate together, or or compress them together or whatever, and then you put it through a linear softmax, get the prediction, which is M. So that's the working part. That's how the encoder decoder architecture based on transformer works. So I hope this is pretty clear. 네, 똑같은 얘기는 여기서 적용할 수 있어요. 여기서도 뭐 빔 서치를 해도 되고 샘플링을 해도 되는데, 일단 기본적으로 요런 확률 값이 나오면 이제 거기서 제일 센 애가 보통 이제 그러니까 어쨌든 확률 값이 나오면 그거 가지고 빔 서치를 하셔도 되고 샘플링 하셔도 됩니다. 그건 디코딩의 트릭 문제고, 기본적인 그 프로세스는 이렇게 된다는 겁니다. 어쨌든 이거가 나와야지 이제 샘플링을 하든 빔 서치를 할 수 있든 하니까, 어쨌든 이거까지 얻어내는 데 있어서 이제 인코더랑 디코더를 거쳐가지고 이제 이렇게 된다라는 걸 보여드리는 겁니다. All right, moving on. So the last part, masked self-attention. I said that here, this part, this is actually masked self-attention, not just self-attention. So in this part, Qkv operations are a bit modified, and the reason why is, right, I guess, okay. In this particular example, we are at the time where we need to predict A. So there's hidden start here. So hidden start IM. So far we've generated start IM, and then it's time to generate A. So in that particular scenario, the decoding process would look like this. So it's given Jesuit étudiant, which are the French words, and so far we have generated I and M. The decoder has so far generated I and M, and it is time to predict A. And there's a question. 네, 좋은 질문이신데 하나의 WKWB로 이용되는 걸로 알고 있습니다. 그게 저도 그 자세한 디테일은 잘 기억이 안 나는데, 이제 일단 여기서 한번 만들어 놓으면 이거 계속 같은 거를 쓰는 걸로 알고 있어요. 그러니까 디코더 1번 블락, 2번 블락, 3번 블락, 4번 블락, 5번 블락 다 똑같은 요 KV를 씁니다. 쿼리들은 달라지겠죠. 쿼리들은 계속해서 이제 이 디코더를 거칠수록 다른 Z들이 나오니까 그때마다 이제 쿼리들의 값이 달라질 텐데, 어쨌든 얘네는 고정입니다. 네, 넘어갈게요. 네. So okay, so yeah, we're given this in French words I and M and time to predict A. In this case, what happens in the decoder block? So this is decoder 1, and here in the very first self-attention, what we have is start and I and M. So we have start, I, and M, and you want to mix and match them together. So basically, this is itself a sequence, and self-attention is there to encode the sequence, right? But we need to be very careful when we encode the sequence, because what happens in reality is when you implement the transformer, you actually set the maximum number of input maximum length of the input sequence, typically like 256 or 512. It's not like RNN. RNN can encode whatever, like the length of the sequence is not a matter for RNN, because RNN can process arbitrary number of input tokens. But when we were talking about transformer, they are actually fixed. So you start with a fixed number of tokens. You predefine the maximum number of tokens of transformer can process, which is typically, as I said, 256 or 512. So in this case, you actually, when you're training your transformer encoder decoder, you put all the English words at the same time. So you put the entire ground truth English words into the transformer, just like in RNN days. Like there's RNN here, there's RNN encoder, and then there's RNN decoder, and then there's like French in, and there's English out. And when we were training, the input to the decoder, RNN decoder, were ground truth English sentence, right? When you're inferencing, you need to when you're testing or when you're inferencing based on your trained model, that is when you predict one word, put this to the next word, then predict another word, put this to the next time set. That's when you inference, when you test. But when you train, you put the ground truth English words into the decoder. Same manner here in the same manner. In the transformer-based encoder decoder, you put all the French words here, you put all the English words, French sentence here, English sentence here, and then try to do a maximum likelihood between ground truth. Basically, this is GT here. This is GT English. This is English hat, and you want to do basically maximum negative log likelihood between GT English and English hat. That's basically, it's the same manner. So when you're training, you put all the GT English sentences into the decoder, and that's when you need to be really careful with the self-attention, because here in the encoder part, in the encoder self-attention, the whole words are already given. It's a fixed information. The whole words are given to you, to the model, Jesui to the end. So there is no problem doing a full self-attention between all the words. But in the decoder part, when it's time, you are at the stage when you need to predict the A. So so far what you have is only I and M, and it's time to predict A. So it is not okay for you to do a self-attention that looks to the future, like this. So when it's time for M to do the self-attention, so you're doing self-attention, so I has a self-attention, M has self-attention, like M has its own attention distributions. And when it's M's turn to do the attention distributions, it is not okay for it to predict or to look into the future. It is only okay to look into itself and its past, but having attention to the future is not okay, because you haven't seen the A yet when you're decoding. So that's why you need a special modification to the whole self-attention, which now you have the masked self-attention because of that. So yeah, this is not okay. This is basically cheating, because your M is already, so when your M has attention distributions to the A and student, which are the future to be predicted words, then you're basically mixing the future information to your contextualized Z's. So when you're obtaining Z, you don't want these information to to be affecting the Z's, because that would be cheating. So, but it's completely okay for the encoder side, because when you're actually testing your model, the French word will always be given in a complete sentence. It's the English part that you need to auto-regressively predict. So that's why you need a special care for the self-attention on the decoder part. All right, moving on. So yeah, so this is okay. So in the M's perspective, it is only okay to look at itself, and it's passed. All right, I hope this is clear. So yeah, so the encoder full self-attention, decoder limited mask self-attention can only attend to itself and backwards. So if you look at the encoder self-attention, then it is like J has attention to itself, but it also attends to Sui, also attends to étudiant. But here, the decoder self-attention, decoder mask self-attention, so mask self-attention, I only looks at itself, but it doesn't go out to anywhere else. M looks at itself and goes back to I. A looks at itself and goes back to M and I. Student looks at itself and then it attends to A, M, and I. So it's unidirectional, basically. So your attention map needs special care. So what happens is, in the mask self-attention, what happens is you already have this from the Qk operation. So Qk transpose divided by the square root of dk. You have that. After you have that, then this alone will already give you a attention strength map, not the probability map, but the score map right before you do the softmax normalization. So you have this, and then you multiply this with a negative infinity mask. So this part is all negative infinity, and this part is all 1. And then when you multiply this mask with your raw attention weights, then what you have is basically like this. So all these will be negative infinity, and these will have its own like certain values, like 96 points and 12 points and maybe 85 points and maybe 112 points, 64 points, and maybe 5 points, something like this, basically. So the points here will be left intact. Here. These will be left intact, and these will all be converted to negative infinity. And the reason that we use negative infinity is only when you use negative infinity, followed by softmax, that's how you get the zero probability. Because softmax is a probability converter, basically. So like if you use, for example, if you have 4-dimensional vector and 6, 2, 0, 0, and you put softmax, you put it for a softmax, then you don't get zero probability for the remaining 2s. You get actually like 80%, 0.80, maybe 0.10, 0.01, 0.01. So simply having a 0 value prior to your softmax doesn't guarantee 0 probability afterwards. You need to convert them to negative infinity so that you can guarantee 0 probability here. So that is why you're using negative infinity matrix here. So yeah, so you do a multiplication between the raw attention weights with mask. You get this, and then you put it for a softmax. Then you get a proper probability map where these are all zeros. These are all like all this is just one giant big zeros here, and then this will have, of course, this will be 1 because it has only 1. It can only look at itself, and then this is like maybe 80%, 20%. Maybe 60%, 30%, 10%, something like this. So basically, you need. So in order to guarantee this, your attention map needs to look like a pyramid or a triangular matrix. 디코더에서 로우 텐션 웨이트가 완성될 수 없는 것 아닌가요? 그게 그러니까 트릭이에요. 이게 사실은 학습할 때는 GT 잉글리시를 다 넣어줘요. 네, 다. 이게 이렇게만 넣어주는 게 아니라 어디 갔지? 네. GT 잉글리시를 다 넣어줍니다. 학습할 때는. 그러니까 뒷단어가 나오기 전이라서 여기에 뻥뻥뻥 뚫린 게 아니라 사실은 I am a student가 다 들어가요. 사실 한 번에 다 들어갑니다. 이렇게. 단지 이렇게 들어갔을 때 어텐션을 걸어주면 치팅 일어날 수 있으니까 그거를 마스크드 어텐션을 극복을 하는 겁니다. 네, LSJ님 되셨죠? 네, 테스트 시엔 당연히 오토리 그랬어요. 테스트 시엔 정답을 모르니까 하나 뽑고 다음 거 넣고 다음 거 뽑고 다음 거 넣고 그렇게 해야죠. RNN처럼. 하지만 학습 시에는 적어도 for loop을 돌릴 일이 하나도 없어요. 트랜스포머는. 김정문님, 로어 텐션 웨이트과 마스크는 엘리멘트, 네, 엘리멘트 와이즈입니다. 엘리멘트 와이즈 해야지 요만큼이 이만큼이 다 마이너스 무한대가 되겠죠. So there was a good question from LSJ. So the question is, how do we get this full attention weights, raw attention weights, when we don't have all the words that we need to generate this attention map? And the answer is, when you're training your transformer encoder decoder, you actually, as I said, you put the entire ground truth English sentence as the input to the decoder. So in this case, you actually have all the words put in to the decoder. So even if it's time to predict A, you don't need to, you already have when it's time to predict A, you actually do have the ground truth English words when you're training your transformers. So what ends up happening is you put all the English sentence into your decoder, and then you simply do masked self-attention to guarantee that your attention maps won't cheat. And that's why you have the masked self-attention, basically. 그때는 오토 어텐션 나온 것까지만. 네, 그렇죠. 당연하죠. 네, 맞습니다. 이제 그때는 그때는 이제 그러니까 이제 실제로 inference. So when you're inferencing, after you trained your model, when you're inferencing, all you have is start. It's not like you're training, so you have the ground truth. When you're inferencing, when at test phase, all you have is start. So you put the start, and then you do a self-attention, which doesn't mean anything actually, because you only have start. And then you have an encoder, decoder attention, where you mix the start with the output tokens from the encoder. So you mix your start with all these, and then predict I, which is the most likely word. And then in the next step, in time step 2, you still have the encoder. You still have the encoder, and then you have the decoder. But now you have start. Now you have start, and you have I from the previous time step. So this is time step 1. This is time step 2. You have I, and then you have masked self-attention. And so in that case, you can't. You do masked self-attention. Now it has some meaning, because now you have I in addition to start. So you have that, and then you have the Z's, internal Z's, and then there you have an encoder, decoder, attention, and that's when you mix these Z's with these. You mix them together here, and then you predict ultimately you predict M, and then in the next step in T3 you do the same stuff again and again and again and again. Yeah. Right. Okay. So yeah. So mask Qkv operation looks like this. So this is softmax Qkv with mask plus mask, or multiply mask, and then you have a proper looking non-cheating Z's as the output. Yep. Okay. All right. Yeah. So this is the end of the class today. So we went 10 minutes overboard. Question. 테스트 시에 인코더 단수만큼 폴롭 돌리는 건가요? 네, 맞습니다. 테스트 시에는 아니 테스트 시에 인코더는 여전히 그러니까 테스트 시에도 이제 인코더 디코더가 있는데 여전히 이거는 그냥 한 번에 넣습니다. 이게 프렌치는 그냥 쭉 넣어가지고 이렇게 다 매트릭스 해가지고 쭉 뽑아요. 그냥 쭉 뽑습니다. 디코더를 폴롭을 돌려야 돼요. 테스트 시에 디코더를. 왜냐하면 한 번에 한 단어씩 뽑아야 되니까 뽑고 넣고 해야 되니까 이제 이때 디코더는 for로op을 돌리고 언제까지 돌리냐? end of sentence가 나올 때까지 돌립니다. 네, 테스트 시에는 당연히 마스크 self-attention은 놔둬야겠죠. RNN 것들 트랜스포먼스 맥 시퀀스 랭스 정해져야 되는 거. 그러니까 이제 RNN 같은 경우는 이론적으로 그 단어의 길이의 개수가 무관하잖아요. 그냥 들어오면 들어온 대로 계속 넣으면 돼요. 그냥 for loop, 그러니까 RNN은 기본적으로 for loop을 쓰면서 계속 업데이트를 H1, H2, H3, H4 계속해서 업데이트를 해주면 되는데 얘는 그럴 수가 없거든요. 얘는 기본적으로 아키텍처 자체가 어딜 보면 좋지? 아키텍처 자체가 기본적으로 이렇게 생겨먹었거든요. 그러니까 여기에 이게 그러니까 애초에 for loop을 돌리지 않고 그 시퀀스를 처리를 하고 싶은 게 그 핵심이기 때문에 트랜스포머는 처음부터 맥시멈 랭스를 정해주고 시작을 해야 돼요. 그래야지 내가 예를 들어서 이거를 이 셀프 어텐션 QKV를 얼마나 크게 할 건지 그 다음에 그렇게 해서 피드포워드가 얼마나 할 건지 이런 것들 다 정해줄 수가 있거든요. 그러니까 처음부터 내가 몇 개의 토큰이 맥시멈으로 들어온다는 걸 정해줘야지 그것만큼 정확하게 매트릭스를 짜가지고 쭉 돌릴 수가 있고 그렇게 함으로써 포룹을 돌리는 걸 방지하기 때문에 그래서 이제 그 트랜스포머는 처음부터 나는 맥시멈 256 토큰까지만 처리하는 트랜스포머를 만들 거다. 나는 뭐 맥시멈 512 토큰까지만을 처리하는 뭘 만들 거다. 이런 식의 그런 걸 만들 수가 있어요. 테스트 시에 GT를 못 넣죠. 테스트 시엔 GT가 없으니까. 테스트 시에는 이 어떤 내가 주어진 불어가 어떤 영어로 나올지를 모르잖아요. 이거 모르잖아요, 이거. 모르니까 GT가 없으니까. 트레인 시에는 안 돌려도 돼요. 트레인 시에는 그래서 디코더, 트레인 할 때는 인코더든 디코더든 하나도 포룹을 안 돌려요. 그래서 빠른 거예요. 그래서 RNN 기반의 인코더, 디코더도 훨씬 빠릅니다. 학습 속도가. 처음에는 그랬어요. 요즘은 이제 워낙 커져가지고, 막 24스택 쌓고 이러니까 이제 뭐 그 성능 차이를, 뭐 속도 차이가 뭐 얼마나 나는지 잘 모르겠는데, 처음에 이제 6스택 쌓고 할 때는 훨씬 빨라요, 이게. 그 GPU로 돌릴 때. 토큰의 길이가 모델 카파보다 긴 문장의 번역을 하게 되면 번역의 품질이 떨어지고, 네, 번역이 안 되죠, 당연히. 왜냐면 애초에 나는 뭐 예를 들어서 512 토큰짜리만을 상정하고 학습을 했는데, 인풋 프렌치가 막 1000 토큰짜리 들어오면 잘려서 들어올 거 아니에요. 그럼 제대로 번역이 안 되겠죠. 그러니까 그걸 나눠서 넣거나, 이제 512를 나눠서 넣거나, 뭐 그렇게 해야죠. 네. 근데 이제 문장 단위로 번역을 할 때는 510이면 충분합니다. 보통 문장이 아무리 길어봤자 뭐 3, 40단어밖에 안 되는데 뭐 길어야 뭐 뭐 50, 한 80단어 되려나? 근데 이제 그거 512 토큰이면은 이게 이제 바이트 페어, 이게 실제로는 바이트 페어 인코딩으로 돌아가거든요. 워드 피스나 바이트 페어 인코딩으로 쪼개가지고 들어가니까 이제 워드 개수보다는 많아질 텐데 예를 들어서 뭐 워드가 50개면은 그거를 이제 워드 피스로 자르면은 뭐 한 3배쯤 뿐다 그럼 이제 150이잖아요. 근데 150도 어쨌든 512보다 훨씬 작으니까 네, 512 토큰이면 굉장히 뭐 아주 양이 큰 웬만한 문장은 다 처리할 수가 있습니다. 네, 구글 번역기 현재 아마 트랜스포머로 돌아가고 있을 거예요. 아마 버트로 돌아가고 있을 거예요, 구글 번역기. 그냥 트랜스포머가 아니라 버트로 돌아갈 겁니다. 아마 구글 번역기뿐 아니라 구글 검색기도 버트로 돌아갈 거고 마이크로소프트 빙 검색기도 버트로 돌아갈 거고 지금 아마 웬만한 건 다 버트가 어떻게든 끼어 들어갈 거예요. 네, 네 알겠습니다. 예. Okay, so if there are no more questions, we'll end the class here. Not tomorrow. Next week is the like the ep, the epitome of the modern NLP, like which is BERT and GPT. Technically, they're not very tricky. It's just using the transformer architecture and just swapping the loss function, and that's it. So it's a very simple approach, but it works brilliantly well. And we'll just hopefully next week we'll be able to end the class within maybe an hour. Yeah. And this Thursday, the practice session will be using transformers to build translation model. So basically, you've already done that with sequence to sequence with attention in RNN, the English to French sentence translation, right? So the training sets are exactly the same. The input and output are exactly the same. It's the French in and English out, or it was vice versa. I'm not really sure. You just need to implement the transformer in the intermediate part to do the translation. Okay, thanks everybody for listening, and I'll see you guys this Thursday. Bye-bye.